So you guys can see my desktop.
Mm-hmm.
Okay, so what we are doing is inductance. Let's see. All right. So what this chapter is about is the following. Let me go to, okay. So let's say you take a straight piece of wire, okay, and then we'll connect it to a battery. Okay, so now this wire, I'm representing it as a resistor, and we connected it to a battery, and this is a variable battery. All right, so now what I'm going to do is I'm going to, you guys have seen these, well, maybe you haven't seen these in a lab, but anyway, I'm just cranking up the voltage on this battery. Okay. So I'm increasing the voltage, and if the wire is straight like this, the current will increase smoothly. Okay, so for instance, if I plot voltage versus current, the current will increase like as the voltage increases. Okay. Now I'll take the same piece of wire and wind it in a spiral like this. Okay, like a solenoid. Let me show you a picture of a solenoid, for instance. Okay, so I take that straight piece of wire and wind it like that. Okay, like this, like that. Again, this is a solenoid. So now I just taken that straight piece of wire and wind it like a solenoid, and now I connect it in a circuit. Okay. And if I try and increase the current, what happens is this piece of solenoid, this straight piece of wire that was wound like that, now suddenly acquires the following property. If you try and increase the current, it'll act like a battery opposing the increase. Okay, so this solenoid will develop a voltage which is opposing this change in current. Did you guys understand that? So it's just before you wound it like this wire, if it was a straight piece of wire, you could increase the current all you want and this wouldn't fight it. The same piece of wire, when you wound it up like this, you try and increase the current, it'll fight that change. And conversely, if you try to decrease the current, the voltage would be in the other direction. Okay, so for instance, here was the current, and if you tried and decrease the current, it would induce a voltage in the opposite direction like that. Okay, so think about that a second. I'll let my dogs in, and we'll get into the slides. Okay. All right, so what we have said is, so here is a solenoid again. You take a piece of wire, wind it up in a spiral like this into a solenoid like this, and this piece of wire in this configuration acquires the property of fighting changes in current. This does not like changes in currents. Okay, so that's what this chapter is about. Okay. All right, so the chapter title is Inductance. And so we'll start off by mutual inductance. Nowadays, we are all dependent on devices that use chips, and chips have many circuit elements in a tiny space. And here's one of the problems that you face. Okay, so let's say here's a circuit, and this is a issue. Well, okay, so here's the circuit, and let's say if this was an AC circuit, then the current is changing all the time. But if it was a DC circuit, when you turn it on and off, as the current changes, the magnetic field produced by this guy changes. And if there's a nearby circuit, the flux through that circuit will change, okay, which will induce an EMF, a voltage in that circuit. So as extra voltage is induced in the circuit, just because it's just because of the proximity to another circuit. Okay, so changes made in this circuit are influencing this circuit. Okay, so it's like, how would you like if your neighbor turns on their their stove top and stuff starts cooking in your house? That's sort of an analogy anyway. I don't know if it's a good analogy, but so stuff is changing in this circuit, and that's influencing a nearby circuit. Okay, that's mutual inductance. And obviously, if the two circuits are close by, then the influence is greater, and so on. Okay. So often magnetic flux through a circuit changes because of time varying currents in nearby circuits. Okay, so this process of induction is called mutual inductance. Okay, so magnetic flux through a circuit changes because of time varying currents in nearby circuits. Okay, so for instance, if you here's an example from the real world. So imagine a large factory floor. Let's say this is one machine, that's another machine, and if there's a lot of machines close by, what can happen is, let's say this machine is running, and then you turn on this machine, and because of the spurious voltage, maybe it might shut this machine off. Okay, and so you don't want that kind of stuff happening, and you have to prevent against that kind of stuff. Okay, so mutual inductance can be a nuisance in electric circuits, since variation of current in one circuit can induce unwanted EMFs in nearby circuits. Okay, so changes in current in this circuit can induce EMF in this circuit. Yeah. Now, here's a good application. The most important application of mutual inductance is in transformers, and that's a very useful application. And we'll talk about that toward the end of the chapter. So here's how we define mutual inductance. Okay, so what this equation is saying is the EMF induced in circuit 2 is equal to, so M is mutual, M stands for mutual inductance, M12, the mutual inductance between circuit 1 and 2, minus M12 dI1 by dt, rate of change of current in circuit 1. So what this equation is telling you is, because currents are changing in circuit 1, you're inducing an EMF in circuit 2. Now notice, if the current does not change in circuit 1, then there's no induced EMF. So if this was an AC circuit, that would certainly influence that. And if this were a DC circuit, when this machine is being turned on and off, it'll influence this circuit for a brief moment. Okay. Now, the mutual inductance is the coupling between the two circuits. You can think of it that way. Now, if of course the two circuits are far apart, then this number will be smaller. Okay. So the mutual inductance depends on the proximity, the configuration, the areas, and all that kind of stuff. So this number is hard to calculate other than for very symmetric cases. But anyway, that's the mutual inductance. Again, now we'll mostly talk about self-inductance. Okay, so here's a solenoid. Like I said, you take a wire and wind it up into a solenoid like this. Now, this wire, because it's being wound up into a solenoid, has the following property. So if you increase the current in that solenoid, induced EMF tries to oppose that. Okay, so an EMF is induced, which is trying to oppose this increase in current. On the other hand, if the current were decreasing, if the current is flowing this way and it's decreasing, an EMF is induced such that it wants to oppose that. An EMF will try and maintain the current constant. Okay. So in summary, a good way to remember this is this solenoid, this wire which has been wound into a solenoid, acquires the property that it doesn't like changes in current. If the current tries to change, this will fight it. Okay, so that's what it'll do. So an opposing self-induced EMF develops as current increases or decreases in an inductor. The self-induced EMF is proportional to the time rate of change of current. What this bullet point is saying is this EMF is proportional to the rate of change of current. You change the current faster, this EMF would be greater. Okay, so that's what that's saying. All right, so again, here's another picture. So you wound up a wire into a solenoid. If you try and increase the current in this direction, this will, while you're increasing the current, it'll induce an EMF in the opposite direction. If you're decreasing the current, this solenoid will induce an EMF in this direction. Okay. All right, so here that's solenoid, and if you try and increase the current, this EMF is given by minus L di by dt. Okay, so it's proportional. The induced EMF in the inductor, L is the symbol for the inductor. The self-inductance is L di by dt. Okay. So again, if the current were steady, di by dt would be 0 and the induced EMF would be 0. So this EMF comes alive only while the current is changing. Okay. And that proportionality constant is called the inductance, the self-inductance of the coil. Okay. And of course, it depends on the configuration of the coil, depends on the number of turns, the area, and so on. The self-inductance is given by mu naught, the permeability of free space, and little n is the number of turns per unit length, and A is the area of cross section, L is the length of the solenoid. Okay, so this is the volume of the solenoid, and little n is the windings number of turns per unit. Okay, the units for L are Henrys, after Mr. Henry, who studied these struct devices. And also you can see from this equation, L Henry is equal to volts. This has units of volts divided by amps per second, which is this. So a Henry is volts second per amp. All right. So for an air-filled solenoid, even though this is showing you that it's filled with something, this is the expression for the inductance of an air-filled solenoid. Now, oftentimes it's useful to have a large inductance. So for the same coil, if you want a large inductance, what you do is fill it with a magnetic material, and then the inductance will increase. Okay, so if a ferromagnetic material is placed inside the solenoid, its inductance increases considerably. Okay. And so mu naught gets replaced by mu m, and mu m is much larger than mu naught. Okay. So there are times when you want to increase the value of the inductance. By increasing the value of the inductance, see the EMF induced is larger, If this increases, the EMF is larger, and then this acquires a larger ability to fight changes in current. Okay. So if you don't want currents to change, if you want to smooth out fluctuations in current, then you would use an inductor to do that. All right, so now is a good time to pause